it is very important that you learn your polyions in order to do what we're doing here. Now, this is very simple. A molecular acid containing polyion is using hydrogen. All hydrogens, for whatever reason in this work, and until I tell you different, there's a hydride, which is a hydrogen minus one. But until we get there, everything is +1 for hydrogen. Okay? And then you will add to that the polyion. And of course, that would be the anion of the nomenclature. Okay? So if you have a polyion of, and I'll come over here, nitrate, NO3 minus, and an NO2 minus. Okay? This is nitrite, and this is nitrate. Now, I want to add to that a hydrogen. How many hydrogens do I stick on to the NO3 and the NO2? Well, only one. It only takes one to neutralize the negative charge. If I had a 2 there, I'd have to put 2 hydrogens in. Well, long story short, it winds up HNO3, and it's of course going to be in water. All your acids. An acid's an acid because it's in water and ionizes. Okay, that's a prerequisite before you can have an acid. And then we have HNO2 is a polyionic molecular acid, and it's in water too. Well, the name of this right here is nitric, N-I-T-R-I-C acid, where this one is N-I-T-R-O-U-S acid. Well, it's really easy to remember these. If you look at your flow chart, your polyions are going to end in ATE or ITE. Nitrate, nitrite. And so you look down here and you learn to, it's a little like sulfur. You don't go sulfurous acid, sulfuric acid, you go sulfuric. So you'll have to make some adjustments. But if the ending is an ATE ending, you drop the ATE ending and you put ic acid on whatever the polyion. If you have a phosphate, it would become phosphoric acid. If you have a phosphite or a chlorite, remember we just showed you the analogous series, chlorite, it would be chlorous acid. So you have to know your polyions, your endings, and then translate that into ATE and relate to ic acid, or ITE and relate to OUS acid. So we'll play with a few of these and see how we do. Okay. So going back to the hydrogen, we're always going to put plus ClO minus. Okay, goes to HClO. That of course is an acid. It takes one hydrogen plus one to neutralize an anion, ClO minus 1. Now, what's the name of it? Well, this is the hypochlorite ion. So if you look on the flow chart, and if it has an ITE ending, you want to change the ending of the polyion to OUS acid. And so this would become hypochlorous acid. See there? And in the same context, if we had a BRO3 minus, just to kind of use the analogous series a little bit, this is a bromate. Bromate ion right there. So looking at your flow chart and trying to remember, well, it's got an ATE ending. I want to change the polyion name to ic acid, and so this would be the formula, and it would be called bromic acid. If you had a BrO4 negative, it'd be a perbromate, and then it would become perbromic acid. See how that works? It's not very difficult, but the critical issue is knowing the polyions and a few others that are quite familiar to you. H2SO3 versus H2SO4. Here we have an SO3, and when this ionizes, what's the breakdown? Well, they always break left to right, just like I showed you earlier at the cation right here. If it's a subscript 2, it will deliver 2 hydrogen ions. You can 2H. Actually, it's 2 hydronium ions, but for right now it's H plus. 2H plus plus SO3 2 minus, and this one does the same thing. It gives 2 hydrogens plus SO4 2 minus, sulfate sulfite. So if you wanted to name the acid right here, and that's a sulfite, what would be the name? Sulfurous, right? So this would be the ionization of F-U-R-O-U-S acid. Very straightforward, and these are widely used, and they're common in literature and work you're going to do in the future. Now this is a sulfate, so it would be sulfuric acid. Now it's not sulfuric, it's sulfuric. So there's some tongue-in-cheek kind of changes that you have to get used to in here. How about HC2H, C2O4. There we go. How about that one? That should have a 2 on it, right there. Okay. C2O4 is what? Anybody remember? Everybody misses this one on the quiz. I'm telling you, 90% of you missed it. And it's oxalate. Okay, yeah, work on that. Yeah, C2O4 is OXALATE. It's the oxalate ion. It's an organic ion. Has two negative charges. It's an organic acid, kind of like that. This is oxalate. In terms of structure, like that. So it's a C2O4 2 minus. So there's a structural formula. There's your molecular formula for it. But why, I don't know. That's just, I guess that's one of those that nobody wants to study when they're learning the polyions. But I'll use it a lot. Okay, so you might as well get used to it. Okay, so this is oxalate. So what would we call that? Oxalic acid, right? You kind of get used to it, you know, as you play with this. So this would be oxalic acid. So getting used to the ATE to IC acid issue is very important in what you're doing. HNO2. You need to know them because there is an HNO3 and an HNO2. And so as you study and experience acids in terms of the types of anions that show up, you have to know who's the ITE and who's the ATE. So this is a nitrite. So this would come out as a nitrous acid, whereas HNO3 would show up as a NIT or IC acid. Now, it's very simplified for you in the context of what I've done here, and will remain the same, and it's consistent for the rest of the book, like that. Now, the true rules, this is not something I dug out. I just noticed the trend and wrote it out like that. But the actual rules of nomenclature depend on the oxidation state of the anion in the structure. They name certain structures relative to the anionic structure. As I show you, I'd rather you keep this in mind, and it is consistent through it for the rest of the future. But if you run into future courses and the professor's just determined to teach you the 46,000 rules and nomenclature, at least you know this one. ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. The front end of the homologous, the analogous series I was telling you about. And the question is, what is the oxidation state of chloride in each of these? Now, this will show up on your test, so try to learn how to do this. Now, for right now, until I tell you different, oxygen's a -2 charge. Okay, write that down 400 times. Never mind. So, oxygen is -2. Hydrogen, till I tell you different, is a +1. So we'll just roll with that for right now, please. So when I look at ClO, okay, and this is called the net charge, which is the algebraic sum of all the charges of the individual elements, right? So if I take the ClO up here, ClO minus, I can break it down to Cl plus oxygen equals a -1. And so I know that oxygen is always -2, so I'm going to put -2 right there equals -1. And this will be my unknown. And so you solve that for X. Very simple algebra. You just kind of spread out your molecule, put in oxygen or hydrogen or whatever you need, and the unknown is listed as next. Okay? So X in this case is a +1. So in the ClO, this is a +1. And this was a -2 for the oxygen. -2 plus 1 gives you a net charge of -1. So this is what I was telling you when we were talking about ionic charges on the periodic table versus ionic charges when you start forming molecules. The conflict, there's a difference in issue starts showing up. And we'll learn why this happens like this when we get into covalent bonding and stuff like that. Right now, just kind of roll with the punch, so to speak. ClO2. Do the same thing for the charge on chloride for here. It will not be a 1. It'll be a +3. Check that out. You have chlorine plus 2 oxygens in this time. 2 minus 2s is equal to a net -1. So solve that one for the chloride, and you'll find out the oxidation state of chloride is a +3. Kind of strange, huh? You're probably not used to that. Okay, and then in this one, chloride plus 3 oxygens, 3 minus 2s is still equal to -1. And so chlorine in this one, chloride, is a +5. Yes, it is. And in this last one, chloride plus how many? 4 minus 2s is equal to -1, and we'll give chloride to be a +7. So it's interesting how that comes out. Now that's one thing you need to learn, because I will give you problems like this. Say, well, in this ion, what's the charge of chloride or bromide or whatever in there? Sum of charges equal the net charge, or if I give you HClO4, what's the sum of charges in that? Okay? When you add up all the charges and you tack a hydrogen on here, you've neutralized the negative. So the sum of charges is 0. So you got a plus, and then a +7, +1, +7, and that's a 2 times -2, -8. So you got +8, -8, 0. If you play with it. Okay, like that. What I want to get to. Now I show you how this is the way the rules. ClO, ClO2, ClO3, ClO4. If you have a structure like this, and this is a +1, this is a +3, 1, 3, 5, 7, +5, +7. When you have a series like this, the nomenclature is defined by rules to be a hypo blank ITE or a blank ITE for any structure that shows up with an oxidation state, a +3 hooked to an oxygen. And this one is a blank ATE. And this one is a per blank ATE. And that's what you'll see in a book full of rules. And so all you got to do is look at this. So if we wanted to name BRO, BRO2, BRO3, BRO4, well, these have the same kind of issue. That's a +3, +5, +7. So if you have a +7, that's going to be a per, what would you put there? Bromate, and so forth. Then, if you needed to make an acid out of this, if it's an ITE ending, is OUS acid. If you needed to make an ATE ending, it would be an IC acid. So if you wanted to name these right here with the ITE ending, this would be hypochlorous acid. Instead of hypochlorite, it'd go to hypochlorous acid. This would be chlorous acid. But now you get down here and you want to name that, what you have to do is you got an ATE ending on it, so that would be a chloric acid. And then there's perchloric acid. And then you got these over here, that would be bromous acid, bromic acid, and perbromic acid, and so forth, like that. Okay, that's a little more complicated now, right? And it kind of gets out of hand. You know. Well, there's a book full of them, about a big set of catalogs that you learn, but you'll certainly get your dose worth in organic chemistry, because they use the IUPAC system almost exclusively to name hundreds and thousands of compounds. For right now, all you got to remember, let's see, it ends in ATE, IC acid, or ITE, OS acid. See the idea? So if you can keep it simple like that for right now, and I won't throw you any curves like this. Now, I will ask you in the course of an exam or something to calculate the oxidation state of an individual element. Okay, like I've got chlorine right here, and I give you the compound with a charge on it. Remember, what is this? A net charge. This oxidation state plus 4 oxidation states of oxygen equals -1. So you make it a little algebra equation, right? You see the idea? Make a little algebra. Oxidation state plus 4 oxidation states equal -1. What did I say oxygen is? What did I say always? -2. Okay. And if you had hydrogen over here, you'd used HClO4, and you needed to figure out chlorine, HClO4. And the question comes to you, what is the oxidation state of chlorine in that compound? Well, hydrogen's a +1. So everything breaks out. Hydrogen, Cl plus 4 oxygens has to equal a 0 in this case, because you've neutralized everything. If you just had the ion, I'd have to put the charge up here, and you'd know what the net charge is, and that would be Cl plus 4 oxygens equals a -1. But they'll both come out the same oxidation state for chlorine. But in this first case, you'd put a +1 plus whatever the oxidation state of chlorine is, we don't know. Oxygen, what'd I tell you? What's oxygen? -2. Good. Okay, good. And so you see the little algebra equation now? Right there. Same way down here, except this is your unknown plus 4 times a -2 equals a minus 1. So now your algebra equation is this one if you're working with a polyion by itself. And I say, what's the chloride oxidation state? And so you chloride is unknown plus however many oxygens, put minus 2. But if you have a hydrogen stuck on there that neutralizes all the polyion charges, okay, you have to take that one into account and put a plus 1 for that, however many. Okay. What's the charge on carbon in here? Everybody wake up now. Come on. I'm about through. So everybody get excited. And I'm going to turn you loose here in a minute. Okay. How do we figure out the charge on right now? Figure out the charge on carbon. Scribble, scribble, scribble. Come on. Figure out the charge on carbon. Plus 3. Okay. So we have a plus 3 charge based on the simple algebra that comes out of these equations. There's only one little set that I'm asking you to try to memorize here, and it's called the homologous series of carbons. And you'll find these right here. And they're based on however many carbons you have in here. Now, when you go to the next level, organic chemistry, you'll be glad you know these, and it won't be so foreign to you. Okay? The IUPAC nomenclature of hydrocarbons or organic compounds is based on this series. This is the homologous series. Okay, of hydrocarbons. And this is CH4 right there. Carbon has 4 bonds. Okay. What if you had C2 and C3 and C4, C5, C6, C7, C8, C9, and C10? Okay. So it's 1, 2, 3, 4, 5, 6. Okay. This one is 8, 9, 10, 12, 14, 16, 18, 20, 22. And naming these things, all of these are in a family of organic compounds called the alkanes. And they are characterized by saturation. They're called saturated hydrocarbons. And what that means is there are no multiple bonds, only single bonds. If you go to double bonds and triple bonds, you change the collective name from alkanes. Say a double bond would be alkenes, triple bonds alkynes, and no. Don't worry about the enes and the ines. Just the anes are your responsibility right now. Systematically, this is the simplest hydrocarbon, and it has a common name, methane. Okay? 2 would be ethane. Ethyl type structures are typically 2 carbon structures. This is a propyl, 3, and is called propane, 3 carbons. 4 carbons is inherently called butane. You got a double bond in there called butene, but that you just kind of evolves, but just to make a point. This one with 5 carbons is pentane, penta. Right there. 6 is like SIX, hexane. 7 is hepta, or heptane. Good old C8 is octane. Nonane, N for 9, and 10 for decane. Now, this is a memory exercise for sure, but you'll be glad you learned them now, because when you go to the next level, everything you name will start out with how many carbons you got. Oh, I got 6 carbons. Oh, that's hexynes. There's a double, triple bond. There's a couple of double bonds, and you got to name on. You throw in a bunch of numbers and stuff. Yeah, it gets kind of busy, but this is the simplest forms. Okay, and I would ask you to include that in your study effort. Okay, so you know, on test day, I'll just probably pick a couple of them and ask you like that. C6H would be what? C6H hexane. Okay, that's it.